Right, so welcome back to Lean Together 2025, and it's my great pleasure to welcome various members of the Lean Focus Research Organization who are going to tell us about their vision for year two. Go ahead, guys.
Great. Thanks, Kevin. Hello, everyone. Yeah, the Lean Focus Research Organization is a non-profit, right? So our mission is to address scalability, usability, and proof automation in Lean. We want to support the formal mathematics community. And the third bullet point is really important. We want to achieve self-sustainability in 5 years. Well, 3.5 now, right? This is important. What does it mean? Is that we do not depend on philanthropic donations after that. We are currently supported with very generous donations from the Simons Foundation, Alfred Sloan Foundation, and Richard Merkin. You can learn more about the Lean FRO in our website, and we have a roadmap that is public. Please check it out. Since the last Lean Together, it's amazing, but it doubled in size. We had 9 people in the last Lean Together, 9. Now we have 18. We are really happy with all new people at the Lean FRO. Please take the time to, all of them are on, you can find all of them in Zulip. Please take the time to say hello. Since the last Lean Together, we had 11 releases of Ling. We fixed many bugs, added many new features, improved performance. It's a lot of work at this point. It's more than 3,000 pull requests have been merged since the last Ling Together. I think the right number is 3,800 something. And since the last Ling Together, Ling appears in the New York Times twice. The first time was because of Google DeepMind with Alpha Proof, and the second time with Harmonic, right? A few months later, they had an article about their company, and Ling was mentioned in this article. We were really happy with in both cases. And Ling is getting really popular in AI, right? So we have this article in Scientific American about how AI will become a mathematician's co-pilot. Terstal gave a talk in Oxford. This is a essay from Google DeepMind released 2 months ago. We're really happy with all this recognition and how people are finding applications for Lean in AI. We want to support all of them. We're also really pleased with all new projects in mathematics. I select 2 here, but there are others. The Fermat's last theorem, we're all super excited about it. There's also the project that Flores started to prove Carlson's theorem, formalize it in Lean. Yeah, this is super exciting. And we're also seeing many new applications, software verification. Later this week, we're going to see a talk about SAMCERT, where Lean was used to verify algorithms used in differential privacy. Jean-Baptiste Tristan is going to give a talk. Netherminds received a grant from the Ethereum Foundation for their work that's based on Lean. We are super happy with that. Last Lean Together, Emina Torlak gave a talk about Cedar. A few months after her talk at Lean Together, she published with her team a blog post describing how Lean is used in the Cedar project. It's a really nice blog post. We have also been giving talks. We gave a talk at CAV about Lean. The content of this talk, we put it in a blog post showing how Lean is used in many different software verification applications at AWS. We also gave a talk at UCLA, a high-level talk for the impact Lean is having in AI. Basically, we try to convey the idea that I think everybody in the Lean community believes that Lean is a single-player game. And because it's a single-player game, people can people are training AI to play this game, and Alpha Proof is an example that they have a really good player for this single player game. Yeah, in the talk we had quotes from Kevin where at one point he was telling us that Ling is his favorite game at this point. But we have many new features, right? I mean, the last Ling together, we announced that Omega was in the oven, it was usable in master, but now since then has been released. It's funny now, it's hard to imagine a day where Ling did not have Omega, right? It's so useful, right? So all of us use all the time. And even if you do not use yourself Omega, you're using it behind the scenes for checking array bounds in Ling, right? Before, it's way more useful, the array bound checking now, because we call Omega automatically behind the scenes. The language server, there are so many improvements, right? Import completion, feedback when you have to rebuild things, you should restart when you should restart the file, information about that to help the user, and more importantly, the completion, right? Mathlib is massive, right? I mean, and many newcomers will start using Lean by saying import Mathlib, import everything, right? And completion was dying at that point, right? It would take, in some cases, 49 seconds to complete something. It's unusable, right? Mark Husinger puts a lot of effort. This is really, people take it for granted, but it was a lot of energy to make this 10 times, more than 10 times faster, right? Yeah, it's way more usable, right? I mean, in some cases, it's almost 100x faster, right? It makes it usable for projects like Mathlib completion. And not just is faster, but it's also more reliable and robust, right? I mean, before, if you had a broken piece of code, completion would fail and sometimes produce results that are worse than the ones produced by Lean 3. And now there are fallbacks that even if your code is broken, it will try to do something useful, right? It's a great gain in productivity for our users. Lake now has TOML configuration files, right? I mean, it's great that you have the Lake file.ling that's super flexible. You can do all sorts of things, but for most projects, you need something very simple. Many people in the community were asking for TOML files that are easy to process, especially if you're building a tool that you want to process these build files for Lean packages. It's great to have a TOML file. It's available, has been released. Many packages are already using it, right? And we're in the process of, even Mathlib will use a TOML file, right? Hopefully. Another great feature that has been merged since the last Link together is functional induction. Functional induction, right? In the past, we lost count how many times people would tell us, do not use mutual. You can't prove anything if you use mutual. It's a pain to prove anything. This now it's completely different, right? Suppose that you have this mutual. Excuse me, Kevin, do you say something?
Not me.
Okay. Suppose that you have these mutually recursive definitions. Before, this feature would be painful. Now Link can generate, you can derive a functional induction principle, right? For example, we are asking here for replace const. This induction principle has two motives. The number of motives is equal to the number of recursive functions in this mutual block that are depending on each other. Sometimes you can have functions in the mutual block. We create strongly connected components, right? For each strongly connected component, right, is the number of number of motives is the number of functions in a strongly connected component, right, in your mutual block. This is generated automatically, and now you can prove something about these functions using this induction principle, and the proof is really compact. And with the proof automation we are developing, this is probably going to be one line in the next link together. Let's see if we can deliver that in the next link together. If in the next link together, we are claiming this is going to be a one-liner, this proof. There are many other tactic improvements, right? I mean, SIMP, we invested a lot of time improving the performance, making the cache more robust, improving the support for literals, right? And providing diagnostics when they are looping. I mean, you can provide SIMP theorems that create a loop, and diagnosing which SIMP lemmas were in the loop was quite tricky in the past. We have now diagnostics infrastructure that makes it much easier. And improving the performance was also important, not just for the math applications, but also for the software verification ones. In software verification, is much more common to have massive goals, right? We have seen goals with more than 1,000 hypotheses, right? I mean, and making sure that SIMP performs well in this kind of goal is important, right, for our future. And I mentioned that diagnostics, there are many different kinds, right? I mean, the set option diagnostics is an umbrella to collect a lot of information. We have this collapsible collapsible information trees, and we collect information about which declarations were unfolded, right? When you're checking definitional equality, heuristics that have been applied and failed, number of terms. For example, here I have an example where we have a loop, right? You have two SIMP theorems that create a loop. You are saying that f of x simplifies to g of x, and you are saying that g of x simplifies to f of x, creating the loop, right? In simplification loop. If you now ask for diagnostics for the SIMP commands, you're going to see that f, eq, and geq have high counters right there. You get the maximum recursion depth has been reached, the error message that you would get in the past, but now you can see exactly which SIMP theorems are being fired many times, right? There's also for type class synthesis, right? You're also going to find diagnostics information there. Like for example, we have a maximum depth, and it's going to say that some in the diagnostics you say, look, this instance failed because the depth has been reached, right? Then you can understand better how to deal with the problem. Okay, this is another great one that people have been asking us for a long time. For instances, you create names for instances automatically. These names should be unique, right? And they should be readable. I mean, sometimes people want to use these names in their projects. And before the promise to guarantee uniqueness, before we were generating names with more than 1,000 characters, right? And people, especially in Mathlib, were very unhappy about that with these gigantic instance names. Kyle put a lot of effort. There's no spec, right, for this problem. You want something that is short but is unique, as it should be readable. You have to find a sweet spot, right? And Kyle tried many different things and finally got to something that is working really well. And in our point of view, completely solves the problem. Displaying large terms is another big deal now, especially in software verification. The goals, as I said, can be huge, and you could kill Ling, the VS Code with a gigantic term right in the info view. Now we have many different flags to control deep terms, the number of steps you get in a maximum number of steps in the pretty printer. And it's not like you don't get enough information. You get these ellipses, right, saying that the pretty printer is stopped here, but if you hover, Ling will tell you what is there. And you can keep doing that recursively, right? I feel like this is a great feature for people manipulating big big goals, right, in the info view, big terms. Another feature that's a recurrent request on Zulip, right? It's mutual structural recursion, right? We had structural mutual recursion by well-founded recursion, but there is a technical issue, right? I mean, when you define something by well-founded recursion, it doesn't reduce well in the kernel, right? And your equations for each case do not hold definitionally. You can prove that tree counts branch xs is 1 plus xs dot count, but it doesn't not hold definitionally if you define by well-found recursion. You may say, so what? But for some users, they are using mutual recursion to define a type. And because you want the type depends, the definitional equality is really important for the type checking algorithm to avoid casts when you're doing type casting. Having mutual structural recursion is really important. You're in, implement this feature, it's great. Also can improve performance. You can tell now, if you don't say anything, Ling will try first structural, then well-founded. But now you can say, I want structure. It's like a contract with Ling. I want to compile this function using structural recursion, and you can select which arguments you want the recursion on. Right? It's even stronger. You're not letting the compile Ling to guess which argument is going to be used for doing the recursion. You are telling Ling exactly which argument the structural recursion should be on. And this is important sometimes, improves performance, and sometimes it's important for how, when you use these functions, right? In this example, is a unary doesn't make a difference, but if you have multiple arguments, it does make a difference. We're going to have a talk later this week about BV decides, but this is really I'm not 100% sure, but I believe Ling is the only proof assistant that has this feature, right? That's is a connection to at least that performs well. I mean, maybe others have, but it performs as well as BV decides. I think Ling is the only one. BV decides for closing goals with bit vectors, right? Henrik is going to give a talk later this week, and he'll give you more details. But today, I will stop with saying BV decides is a very unique feature we have in Ling. It's performance, and people are using it all the time for. This is super important for software hardware verification. Another feature that's I'm a big fan. I mean, Kyle implemented this feature before the syntax for setting configuration options to tactics like simp was really verbose. I would, for example, I would never use it. I mean, I would. I'm too lazy to write this whole thing. I would try to figure out a way to prove without having to set the configuration options. But now it's super convenient. It's much more compact. For Boolean options, you can use plus and minus. Plus is to set to true, minus to set to false. You don't need the config anymore. And it's consistently used in all tactics that have configuration options, right? It's very generic what Kyle implemented. and it's easy to use. I mean, if you implement your own tactic, you want configuration options, use the infrastructure that Kyle built. It's it's great and makes it super easy to use configuration options, and completion works. It feels like magic. I mean, I probably Kyle spent a lot of time to make this work because it's beautiful. The standards library, we made a lot of progress there. We have hash table data structures that are, we have dependent hash maps, hash sets. Uh, a lot of care has been put on making sure these implementations are efficient. The structure updates are performed when possible, right? All core functions are fully verified. You have all these lemmas available to prove properties about your code. We also merged a date and time library. We have now includes types for timestamps, duration, clock, time zones. This is also a foundation for more advanced features like the asynchronous I/O library that we're currently developing. And we have now a rich library of terms for lists, arrays, and vectors in the standard library. And just to give you a high-level example for the standard library, here's a small example where you are trying to write an efficient function for erasing duplicates using a hash set. This is asymptotic linear time, right? The idea is that you are storing in a hash set the elements you visited so far. It's a simple piece of code, and it's not that hard to prove that this fast version is equal to the inefficient one, right? I mean, all the lemmas about hash sets are all being used behind the scenes here. It's great. I mean, to have a library and a verified one with all the useful theorems, you can prove properties like that without spending a lot of energy proving auxiliary lemmas about the data structures that are available in the standard library. And here's a small example for the date and time library. For example, you can get the current time. You have operations like add 4 hours, and you can ask to format, and you get a nice output. The Lean FRO is still sponsoring the MAFLi Cash. It's unbelievable, but in the last 30 days, it's around 6.5 terabytes of data have been served, right? We now have a triage team for all last year we created this team to go over all the issues. The main mission of this team is to first put in categories all the issues, right? Assign if it's high, low, or medium priority. If something is high priority, someone in the Lean team will take care of this as soon as possible. Like even if they have to drop what they are doing, they will address this issue. By median, maybe you have to wait another quarter to, or one or more quarters to get to see a fix, and low is basically saying, well, in a future when all the missing pieces in Lean have been implemented, we will address this issue, right? Here we have a graph showing the progress of the triage team. We plan like in the end, in 3 months, 4 months from now, the whole backlog will be done, right? We'll have categorized every single issue in the Lean website. Live.leanlang.org is also great for supporting learners, people learning Lean, supporting courses. We have seen sometimes 84 concurrent users, and we doubled the amount of memory to make sure that we can support this kind of load. And we're discussing how to improve this service in the future. Google also is really popular. I was blown away when Johan came up with this metrics, 180,000 queries per day. I was blown away. I knew it was popular, but I didn't know it was that popular until Joachim shared this graph and this data with us. In our roadmap, Joachim, Sebastian, David, and Kim will tell you more about what's going on, our future plans, but the highlights are parallelism will reduce both editor latency and build times. We will have a complete reference manual in 2025. We are going to develop a module system. We are working on the new code generator that will make sure the Ling binaries are smaller. You make sure the generated code is faster. There are many UX improvements in the oven. Some of them I bet the community will love. They address things people are complaining about. We're going to have better frame functional interface support. There are many new features and improvements to the standard library. We are working on endgame tactics, in two endgame tactics. One is BV decides and another one is grind. We are going to see a lot of improvements in both of them in 2025. We are planning to have support for monadic code reasoning. People that are on Zulip probably see from time to time people complaining that if you use the do notation, it's great for writing code, but it's a pain to prove things about this kind of code. We want to fix that in 2025. And we're addressing Mathlib refactoring technical debt reduction. Now, Sebastian, I can start clicking. You say click and I will move ahead.
Perfect. That would be great. Thank you. Right. Yes. So with the start of the FRO, we were able to invest in some fundamental elaboration, refactorings and extensions. And yes, on the next slide, the first result from that you've hopefully already seen in your editor. That was the incremental tactics, which does exactly what you see on the right. Now, when you have a theorem, a tactic proof in Lean, since they've quite a few versions, you get this incremental display of the progress through that as Lean goes through that theorem. And even more importantly, if you do a change somewhere in that theorem, then of course we only start re-elaborating that proof from that point on. And so yeah, that is already supported today in all theorems. If you start them with by, and then for all the most common combinators, it just works. And yes, so I have in total, there has not been that much feedback on this issue. So, and there have not been any bug reports anymore and recently. So I do hope that this just works. If it doesn't, please tell me about it. Yeah, but looking forward, we use the same infrastructure, not only for incrementality, but now we're working on parallelism as well. So on the next slide, Leo, could you go to the next slide? Yeah, thank you. Yes, parallelism, again, is what you see on the right. So now if we look at multiple theorems, then of course, on a modern machine with many cores, yeah, why not process these theorems in parallel? And as you can see, that of course combines with incrementality. So for each theorem, you get incremental results in parallel to others. So at this point, Lean free veterans might say, oh, didn't we have something like that in Lean free? Yes, that's correct. It looked something like that. Well, you didn't have incrementality, so it didn't look quite as nice as here. And in general, we had a relatively simple system for making this work in Lean free, I should say. But Lean 4 is a much more complex system now. It has to be because of all the extensibility that we provide to create all your custom tactics and so on. And yeah, so we're now taking a more fundamental approach to implementing this parallelism. And so actually we're going through many steps right now to get this shipped, get this to your local Lean installation. We've started with putting all the linters on a separate thread, making them asynchronous. That's already in the current master branch at least. Next step will be, let's put the type checker as well on a separate thread so that we can already continue with the next theorem after that. Let's do the same thing for the code generator, for definitions. And then after these preparatory steps, we can say, okay, and now we can put the proofs as well on their own threads. And these steps are already implemented. What you see on the right is not just some some visualization, but the actual thing. Now we just have to actually land that in Lean Master and then in a release. And so that's the step we have currently planned. This new infrastructure would allow us to go even further. Like we will evaluate, should we also parallelize definitions and so on. Like there's no real ceiling here. But yeah, that's these 4 steps. That's the immediate goals also for this quarter. And since we're talking about goals, I should also say, first we'll focus on reducing editor latency, because if you don't have to wait for all the previous theorems to go through, then the entire system is just more usable in the editor. And we do also want to improve build times as well, as Leo mentioned. Which is just a bit more complex because Mathlib is already very parallel, for example, because it has so many files. So it's actually, you actually need to be careful if you make any changes there that it doesn't get slower in the end. So yeah, first the editor, then the build times. Okay, I think I have one more slide on what to expect here. So yeah, just to show that yes, something is running in parallel here. That is one profile visualization of such a file running through this new system. And yeah, in fact, this is the trace profiler, which has been upgraded to also be able to visualize such files now running in parallel. And then you can really look at it in detail. Oh, this theorem is running in parallel to this theorem, and so on and so forth. Okay, so if you're a meta programmer, at this point you might be asking yourself, so what does that mean for me? Will I have to start from scratch? Fortunately not. On the next slide, I've summarized that. So even if you do some somewhat advanced things like creating your own environment extensions, it should simply work without changes. So even if like you're inside, you have a tactic inside a proof and it's setting environment extension state there, and then you're reading that state outside that proof, it will just continue to work. We don't want to break anything here. What that does mean for that to work is that if you do such an access, it will wait on the previous proofs, because that's the only way we can do that without breaking anything. But then we will on top provide API so that for your environment extension, you can opt into asynchronous support, so that you're saying, okay, for this access, I actually don't need to wait on all the previous proofs, for example, because I don't actually use my extension in proofs. Or even more specific, wait on that specific proof, which is of course the exact same API that we're using for our extensions. So yeah, the exact API hasn't landed yet. I can't show it here yet, but yeah, that would also be too much detail for this talk. So if you're interested in that, please look forward to the specific PRs. And that should be it from my side.
Cool. You're him?
All right. Can you see that?
Yep.
Great. Okay, so I'm going to show you a feature that I'm working on. Will be landed in a few weeks or even sooner. And if you know my previous work, you won't be surprised that it's all about recursive function definitions. So here's a function definition that's recursive, and it's typically a non-terminating function. It's basically the while loop implemented as a recursive function. So as long as f applied to x returns something, we keep going until it stops returning something and we return that value. And that we can define in Lean, but we have to mark it partial, which means for the terms of the logic, it exists, but that's all we know about it. But we can still compute with it. We can compile it, we can run it with eval, and here we can run the loop, basically counting as long as the number is less than 10, yeah, and then we get the 10 out. So that works. But what if we do want to verify something about this function, want to know something about this? So far we couldn't do this. Now what we can do is we can say it's a partial fixed point. With a new keyword, you put it in the same position as you would put the termination by, and suddenly Lean is happy with that definition. And we can even prove things about it. So here we have a proof that as long as basically the function we pass to while always returns none, so this is essentially while false, it doesn't change the value. And that now works. We can also prove something about, we can also verify the computation that we just did in line 11 as a theorem. We have to a little bit wider. We can't just use simp while sum because that'll send the simplifier into an infinite loop. But if we just do it a bit more careful and we say, well, apply one step of the function definition and then simplify, then this actually works. Now, I expect that some in the audience will now feel very worried because you've learned that Lean is this language of total functions and you have to always prove termination. So what's happening here? Now, I can assure you we're not changing the logic of Lean. We don't threaten soundness here. But if you think about the partial keyword before, that's where we said there exists a function of this type, but you don't know anything about it. Now, what we do here is a bit of a middle ground. We say towards the Lean kernel, there exists a function of the type while sum, and it satisfies the equation that we give there. But for all the things where the equation doesn't really tell us anything, we don't specify what the function looks like. So for example, we will not be able to say anything about the behavior of the while sum function on when we basically have while true, the infinite loop. But which basically saying there exists some arbitrary value in the sense of classical choice that will satisfy this equation. So this also means that in order to not endanger soundness, this only works if the function type is, the type of the function is inhabited a priori. So we first have to prove to the kernel that there exists something of the type, and then we can go on and say that it has the properties we want. So if we try this to find this rather similar function that goes through the natural numbers to find the first one for which f returns a value, then it can't do that, and we'll get an error message. So soundness is not in danger. If you're coming from a background of, let's say, Isabelle uses, then you may find this completely benign and not very surprising, because it's a feature that Isabelle has had for a long time, and it was about time that we have it too. In general, the rule here is that any function type, or any function where the type is inhabited a priori, which we need for soundness, and where all the recursive calls are in tail position, any function satisfying these two criteria, we can, or any function definition satisfying these criteria, we can just accept, and that works. And we get equations out, and we can use these equations to prove the behavior of the function on certain inputs. We can even go a step further. There's a second component to this feature, where if the function happens to be monadic, so defined in the option monad, then basically any function definition works. It doesn't have to be tail recursive, as long as it's basically using the monadic combinators to assemble the function. So it doesn't have to be tail recursive. And what we get in this case is even more. We not just get the equation of the function as something we can use to talk about the terminating inputs. We even get a correctness theorem that allows us to deduce something when, maybe one step back. So the trick here, or what we can do for an option monad, is that if basically when the function isn't terminating, then this is defined to return none. And this means if we have by some other way, we know that the function is returning a value, we know that it's an input for which it actually terminates, and then we can deduce something from it. So we have this partial correctness theorem. It looks a bit scary, but it's not too bad actually. And we can use it to, for example, prove that if the while loop returns a value, then the condition actually on that value of the result returns none. Right, so the two benefits are we get the partial correctness theorem when we use monadic code, and then basically any function works. So for example, Ackermann function, we could prove termination for that too since a year or so easily, automatically, but we wouldn't have to if we were to use the option monad and this feature. And then also stuff like nested recursion works. So here we have a tree data structure where a tree is a list of trees, and we define functions using higher order functions like mapm on lists, or here even with a do notation and iteration. And all these kind of patterns are just accepted reliably and give you something to verify. This may be less interesting for the whole Mathlib crowd, where we rarely have complex recursive things. But this is very interesting, I think, for everybody who wants to do program verification. And as a point to demonstrate that is that the Aeneas library, which can be used to translate Rust code to Lean to verify it, basically had this construction inside for a while. And basically now we're giving it to everybody. That was a quick demo. I'm planning to not release this before we have the manual section for it written, which I think is a great transition to the next topic.
Awesome. David, I'm going to share the slides.
That's great. And I will use the word click as requested at the beginning.
Great. Go ahead.
Hello, everybody. I'm going to tell you a little bit about our newly released reference manual. Please click. 1 year ago, at a conference very much like this one, click, there was a talk given by me with the title Documentation as a DSL, which talked about big dreams for how we're going to go and write documentation for Lean in Lean. And at the time, I showed off a sort of early prototype of a documentation tool which let you use a markdown-like syntax as part of a Lean file. And we revealed our new website, which is all done in Lean now. And, or at least, yeah. And we talked, I presented some plans for how we're going to get to a user manual and some of the features we want to have. Please click. Where are we today? Click. Today, we have a language reference manual that you can go read. It was the first actual release happened just before the winter holidays. So 2 days less than 1 month ago. That means another release is going to be pretty soon. It's built entirely in Lean using Verso. The content interleaves the doc strings drawn from the source code with explanatory material that puts them in a context and explains the fundamental ideas and the ways they interact with one another. The release that you can go read right now that's publicly released contains 88,647 words of fresh content in addition to the doc strings. Depending on assumptions about page layout and font sizes and things like that, that's somewhere from 150 to 200 pages. The development branch is at 93,620 words, and there will be more soon. The whole thing is being designed for sustainable maintenance because out-of-date documentation is not necessarily a useful thing to have. So it's full of machine-checked examples. These are examples that illustrate the concepts being described, but a side benefit of them is that if the concepts being described change, the examples will stop working and we'll find out about it so we can update the text and the examples together. And furthermore, there's a lot of inline tests behind the scenes that'll tell you that'll tell us if any of the claims we make about the language are no longer valid. One fun example of this is that I discovered that structures had become recursive because next to the sentence in the chapter on structures, there was a little remark that they weren't allowed to be recursive, and I had a test to verify this. And that test suddenly started failing when I updated the Lean version. I thought, yes, and it was a wonderful sentence to delete. Thank you, Kyle. Click. So what is a reference manual? Just so, like we've made this thing, what is it that you can use it for? It's probably not a good first learning resource. Maybe if you have deep experience with related systems, then this would be all you needed to sort of get up to speed on how things work. But it's not the intention of it. It's also not a full formal specification of Lean. That would be too voluminous and not actually all that useful because usually you don't actually want every detail. You want the right details. Click. So being a reference manual, what does that mean? Like, what does that look like? Click. One thing we have is, tables that do things like match the syntax extension repetition operators to the things used in anti-quote splices to match against them. Click. It also means that we have text that specifies the precise rules for decreasing parameters for structural recursion. This one written by Joachim. Thank you. Click. It means that we have diagrams giving the runtime representation of various primitive types, where that is different from the standard rules for inductive data types. Click. It includes snippets of grammar for various parts of the Lean language. One thing we can't see, unfortunately, in Google Slides is that if you put the mouse over these various syntactic constructions it is mentioning, you get docstrings for them. Click. And because this whole thing is built entirely in Lean, we get our example rendering gets to be very intelligent and know a lot about the code that it's showing you. So there's an example of subgoals here. And so we give an initial proof state, and then we say we're going to run this tactic, cases H, and we're going to get these two further goals. The source code of that section of the manual is over on the right. And here we can see that I wrote down some Lean code, and that Lean code turned into the hyperlinked hover containing code on the left. Also, I wrote down what I expected the result to be. So actually, the result shown in the source code is not the one being rendered over there. That one is just produced by running the tactic. But having it there means that if I click, delete one of the two cases that I'm expecting to see, that my readers are expecting to see based on the text, I get a red squiggly as the documentation author. Not only do I get a red squiggly, because that's not always what you want, but I get a little light bulb next to it. Click. And now I'm gonna not. This is not a click. When I click the light bulb, I get a little pop-up which offers to fix the example here because maybe that should just be the right thing. Click. And we get very accurate descriptions of the code. So in this example, which is showing how the if tactic works, or if in the tactic language works, we can see that we can see proof states by hovering and such, but also the little underlines on the ifs lead you to different parts of the documentation. So there's the if on the same line as the word example, which is the term level if, which is like how you split on the result of a decidable proposition. And then there's if in tactic mode underneath the by, and that one allows you to do reasoning by cases based on whether something is true or not. And those are actually different structures in Lean. And because we are so tightly integrated with all the tooling, it happens for free, that all of these links take you to the right place while you're reading the documentation, if you're ever curious. Click. So what's next? Click. We have a contractor who's working on a search interface that takes advantage of the big table of metadata that's collected while building the documentation. So here, if I go into the search box and I type ind, then I get things like array.indexof. I get terminology, so all the jargon used in the manual is annotated as such, sort of both at the definition site and reference sites, so we can link to the definition site of vocabulary or terminology items. We have section headers like indentation, and so on and so forth. And this category can grow over time, should that be interesting. Click. Another feature that's showing up is that in the current release of the manual, most of the doc strings don't have these nice features I've been talking about because they are written in Markdown. And in Markdown, you don't have a way to say, this is the name of a tactic versus this is the name of a term, or this is a proof. And so the upcoming release will contain a set of heuristics, which essentially try to work out what was meant and make it work. It's not 100% accurate, but it's certainly better than nothing. Over time, we're gonna annotate these so that they actually give the right information. But in the meantime, it's really nice to have the hover work on list.toArray here. The heuristics used here can also serve as a means of informing the review of it to make it much faster. So it's a code action rather than a sit down and type a thing and figure out what's meant. Click. And of course, the most important thing, more content. I'm in the process of writing the chapter on Lake. Max helping out with reviewing that as we go, telling me what I've misunderstood. Chapters on coercions are coming up. We're going to get quotient types and much more of the standard library. And if you want to follow along, it's all open up. It's all open. You can go take a look. If you find a typo, you can send a pull request to fix it if you want, or open an issue and I'll fix it. And please, if there are things that you're blocked on not knowing about, open an issue or upvote one, because that will be taken into account for planning. Like we have a fixed idea of what's coming immediately, because these are sort of obviously high priority things, but the more we get, like as we get further along, then finding out that this description of this would unblock this user is a very useful thing when we figure out what next to prioritize after the immediate priorities are done. Thanks very much for listening.
Great. Thanks, David. Kim, are you there?
I think Kim is not there, so
Okay, okay, Johan. Great.
Yeah, so I want to say a little bit about the Mathlib side of things. Kim and Anna and I have been working on that. So click, I guess. Right. So we've been working on several things, and to start with a whole bunch of technical debt that Mathlib has acquired over years, and mainly during the port. We discovered a lot of issues, or maybe punted on a bunch of issues, but we were quite diligent in making notes of all these issues, and so there are thousands of porting notes in Mathlib, and by now we did get rid. We classified a lot of them. Pietro Monticone has done a wonderful job of doing a lot of that, and we've started really resolving these, but there's still a lot of them around. We also have adaptation notes, which are notes that we introduce when we bump to a new version of Lean, to a new Lean release, and this maybe introduces a lot of new cool features, but there are some edge cases in Mathlib that maybe abused something that is no longer possible to abuse, and then we make an adaptation note saying, look, this no longer works, and maybe we have a fallback feature, fallback option, and we use that, then we should get rid of that. So these are all sorts of technical debt that we want to reduce, and we have been reducing in the past year. One example is max heartbeats. So whenever Mathlib needs to use more heartbeats than the default, we set this option, but we want to get rid of them. I think there are at the moment 17 places in Mathlib where we use max heartbeats, and we really want to get rid of them. There is e-rewrite, which is an expensive form of the rewrite tactic, and which usually indicates that there is a missing simp lemma or some other unfolding lemma that is missing. And using e-rewrite can be a great hammer to make progress on your goal, but it typically also leaves you in a state where other tactics like simp and rewrite no longer really work because, well, even though your term is still type correct, it's syntactically no longer in a good shape where other automation can kick in. So e-rewrite is a bit of a code smell, or quite a bit of a code smell. We've been removing many of them, and we plan to do a lot more, especially in the upcoming quarter. We want to get rid of a lot of this technical debt. So this is sort of negative things that we've identified in Mathlib and have been working on removing them. But at the same time, there are also positive things that we've been trying to improve in Mathlib and that we're working on. So we've created a lightweight spine of files that only contain definitions and no theory, or very little, like only the really, really basic theory about these definitions. And so far, this has been done for the basic algebra hierarchy. So a benefit of this is that you can import lightweight files without all the theory required to prove theorems. And this improves parallelism. It also improves debugging when we hit a problem in Mathlib and you want to minimize the problem, then going down to this spine of definition-only files means that there is only a very small fraction of Mathlib that the problem depends on. And we'll continue this upwards through the finiteness hierarchy and some elementary analysis and topology. And then there is also the refactor of concrete categories. Christian Merten and Anne have been working on that, which will greatly improve the way concrete categories can be used. And yeah, this is really important for several parts of Mathlib, especially algebraic geometry and algebraic topology, where these issues were really impacting the way we could formalize parts of mathematics. And then on the side of infrastructure, there's a pretty complicated system. When people work on Lean core at the FRO, then they might want to test how does this feature impact Mathlib. So you need combined continuous integration between the Lean 4 repo and the Mathlib repo, and automatic juggling of branches that use different tool chains, and things get updated and tested, etc. And there was quite a bit of manual work involved there, and a lot of this has now been replaced by happy little bots doing the work for us, and scripts that tell you how to merge bumping PRs and testing PRs, etc. When dependent PRs in the Lean 4 repo have been merged, then we get notified that something in Mathlib has to be merged as well. So this is very convenient. Yeah, and then finally, I think one more slide. So yeah. Okay, so one thing that I've been working on, and this is joint work with Michael Rothgang, is a Mathlib review and triage dashboard. And I don't actually want to say too much about this. I mainly want to make use of this slide as an advertisement for the talk that Michael is going to give on Thursday, I think. But this is a website that we use, that we've been working on, that greatly improves the workflow for reviewing Mathlib PRs, and it gives insight into a bunch of data that is not visible via the usual GitHub dashboards. That's all I'll say about it for now. You should go to Michael's talk to learn a lot more about this dashboard. That's it from the Mathlib side.
Awesome.